If I look at this graph and I'm asked to work out the velocity of the car at 20 seconds, at 20 seconds the car is going at a totally unknown speed. I do know that it started moving at 30 meters per second in an easterly direction, and then I've got some negative acceleration at -2, I've got some positive acceleration. So I'm actually going to have to calculate out the answers over here. So I'm going to use v is equal to u plus at. My initial velocity is 30, and I am accelerating at -2 for a period of 10 seconds. That means that my final velocity is 10 meters per second east, and that's true at 10 seconds. For the next 5 seconds, we can say velocity is equal to the initial velocity of 10 meters per second plus a positive acceleration of 3, and that is true for 5 seconds. And I land up with a positive answer again, so it's still going eastward, and it's 25 meters per second east. And that's true at 15 seconds. And finally, I can say for the last 5 seconds, final velocity is equal to starting velocity at 15 seconds plus there's no acceleration for the remaining 5 seconds. So in other words, it's still going at 25 meters per second east. And I've got that as an answer option over there as D. During the 20 seconds, the car is stationary when? Now, if I take a look at what has happened to this car, it has gone to 10 meters per second, so it's slowed down, then it's speeded up again, and then it stayed at a constant velocity, but it actually never stopped. So it has been stationary, never. A ball is tossed vertically upward. It reaches its topmost point and then falls back to a starting point. While the ball is in the air, what is true? Now, we're talking about projectile motion here. Objects go up, they stop for a second, and they come back down again. The starting velocity is exactly equal in magnitude, but opposite in direction to the final velocity, and I land up with the object standing still at the top of its projectile, and it is under acceleration for the whole time of exactly 9.8 meters per second squared. So, the acceleration is always in an upward direction. Well, the acceleration is actually always in a downward direction, so B seems to be a pretty good answer. We might hang on to that. But let's check the others. The acceleration is always in the same direction as velocity. Well, let's think about that. On the way up, my velocity is upward, but my acceleration is downward. So that isn't true. The acceleration is always in the opposite direction as velocity. Well, let's see. On my way downwards, my acceleration is down and my velocity is down. So therefore, that isn't true either. So the only correct answer is B. For a vehicle moving in a straight line, which one of the following physical quantities could be determined by finding the gradient of a displacement time graph? The gradient of a displacement time graph is always the velocity. So I go looking where, and there's only one velocity option, so it's the average velocity. And finally, study the velocity time graph of a vehicle traveling in a straight line for 8 seconds. What does the shaded part represent? Okay, so this is a velocity time graph, which means that the area under the graph is going to be equal to the displacement of the object. If it's all in one direction, then I can even say it's the same as the distance. So it's the distance it covers in the first 4 seconds. That seems like a pretty good answer. It's the total displacement of the whole trip. No, then I would have needed to have worked out this part as well. And the change in displacement during the forward trip, that's not a totally unreasonable answer, except that it's also got the distance. It's very clear in that the distance it covers in the first 4 seconds has been shaded over there. So I would go with A as my most correct answer there. If I relook at D as well, there is some merit in the idea that they would have to probably arguably give you a correct answer for either A or for D. We now have a 4-meter long car. It's approaching a robot. I've got an initial velocity, and I have got the front end of the car at 42 meters. So I need to consider then that if I were to take a look at this, you've got the car, which is 4 meters long, and until the robot, you've got another 42 meters. So in order for the back end of that car to get past the robot, I'm going to need to, in total, go 46 meters. Let's just keep that in our minds. The green light changes to yellow for 3 seconds and then to red. The driver decides to try and beat the robot. Gets the whole car past the robot before it turns red, in other words 46 meters, and accelerates the car uniformly at 3 meters per second. Firstly, prove that he cannot possibly beat the robot if he does not accelerate. So it's pretty simple. I'm going to work out a distance that if he went from at a constant speed of 10 meters per second, so we take the original velocity, we do that for exactly 3 seconds, and we find that we get past 30 meters. Well, when I compare 30 meters to 46 meters, therefore he can't. It's much further to go 46 meters than the 30 meters he would have covered if he didn't accelerate at all. Remember that if he doesn't accelerate, I can use the very simple equation which comes from the triangle you've learned from early days, and that is that velocity is equal to displacement over time. So if I'm looking for displacement, I would cover up the displacement, and I see that it's velocity times time. Does the driver, by accelerating at 3 meters per second squared, really beat the robot? Show the calculations to substantiate your answer. So now we do have acceleration. I'm going to use an equation of motion with S is equal to ut plus a half at squared. I have time, I have acceleration, I have an initial velocity of 10. The time that the robot's changing is 3 seconds. My acceleration is a positive 3 seconds, and 3 squared. Substitute that in and I get 43,5 meters. Well, again, 43,5 meters is still less than 46 meters. So although he might think he got past the robot, because the front end of his car did get past the robot, the whole car has not managed to make it past the robot. Finally, assuming that the car is still accelerating as the robot turns red, calculate the speed of the car at that point. So I am now going to say my final velocity is equal to my initial velocity plus acceleration times time. I started at 10. My acceleration was positive 3 meters per second squared. I am doing that for 3 seconds while that robot's changing color, and I am at 19 meters per second. Use the following information in order to draw sketch graphs. You have to draw a sketch velocity time graph for a car moving on a straight horizontal road. Show all your calculations and label some key values on the axes. You get given a starting velocity, you get given acceleration values, you get given another acceleration value, and then you can start working out some information. So let's try and sketch that graph. The first thing I need is an axis, and I'm going to say that it's time in seconds, velocity in meters per second, and I've got a 0 value over there. I am told that my starting velocity is 25 meters per second, and I keep going at that speed for 40 seconds. Then they say to me that over the next 50 seconds, there's a uniform negative acceleration. So let's see what happens. Where is that going to land up as my final velocity? So final velocity is my starting velocity plus acceleration and time. I've got a starting velocity of 25 meters per second. I'm slowing down at 0,5 meters per second squared, and I do that for a length of time from 40 to 90 seconds, and from 40 to 90 seconds is going to be 50 seconds. So I get an answer of exactly 0. which means that when I bring that down to 90 seconds, it's going to stop at a velocity of 0 over there. What is the state of the motion of the car at 90 seconds? Well, it has no velocity, so it must be stationary. By using the graph only, determine the distance travelled by the car during the first 90 seconds. If I've got a velocity time graph, I can determine the distance travelled by the area underneath that graph, especially if it hasn't changed direction, then it's just distance is displacement. And I am then able to say displacement is equal to area under graph. And I'm then going to say the rectangle is 25 times 40. So I've first worked out the rectangle. Now I've got a triangle that I need to work out, plus half of base times height, half of 50 times 25. My 50, the base of the triangle, 25, the perpendicular height of the triangle, and substitute that through and I get 1,625 meters. Draw a sketch of the corresponding displacement time graph for those 90 seconds. So what happens in a displacement time graph for those 90 seconds? I better label my axes, time, seconds, displacement, meters. And I find out that over the first 40 seconds, if I just work out that portion of the displacement, that portion over there, I would have landed up at 1,000 meters, because 25 times 40 is 1,000. And that would have been after 40 seconds, and it is traveling at a constant velocity. So on a displacement time graph, constant velocity is represented using a straight line. So that, as you can see quite clearly, is a very straight line. And then you are going to say what happens over the next 90 seconds, at least next 50 seconds, is that this particular vehicle slows down, the gradient gets less and less and less and less until it is horizontal by the time we reach 90 seconds. And by that stage, it has gone 1,625 meters along.